So the purpose of this video is we're going to have a wee chat about Newton's laws, first of all the linear ones, and then you guys are going to have a go at transferring them over to make some rotational versions of Newton's laws of motion. Just to remind you, number one, an object at rest will remain at rest so long as no net force acts, and an object in motion will stay in motion at constant velocity so long as no net force acts. We just wrote it shorthand there. Second one, F equals ma, F net is equal to ma. And the third one's the one that we all know. For every action force, there exists an equal and opposite reaction force. Two different forces acting on different bodies, same size, opposite directions. I want you to pause the video and have a crack at writing them out rotational version, but be warned, there are some fish hooks. Okay, there's the first one. Hopefully you all worked out that it was angular velocity that stays constant instead of linear velocity, but a bit of a fishhook there with the net torque being equal to 0, and that's because if we want to make an object rotate, we don't push it, we twist it. We apply a torque and not a force. So, if you got that one wrong, correct it, and go and make any changes you need to the subsequent two. Pause the video if you want to make those changes before we go on to the next ones. Now the second one's probably the trickiest of them all. Tor equals I alpha. It's not much stayed the same there, was there? The torque, let me just add in a wee net there. The net torque is equal to the rotational inertia times by the angular acceleration. Well, we've met angular acceleration before. That's the rate at which a rotating body changes its angular velocity. But the rotational inertia, what does that mean? Well, that's our equivalent of mass. But it turns out when you want to make something rotate, it doesn't, how hard it is to change its angular velocity doesn't just depend on the mass of that body that you're trying to make rotate. It also depends on how that mass is spread about the center of rotation. The further that mass is from the center of rotation, the harder it is to make that object rotate. We're going to look at this a whole lot more later on. Inertia, there's no easy way to calculate. Every different shaped body, there's a different equation for calculating up what the inertia might be, taking into account the different spread of the different parts of the mass about that central axis of rotation. And I'm going to send you a link with some details of the basic ones. We'll have a play with them. Have a go at that third one if you haven't already. Okay, so the third law is that for every action torque, we need to have an equal and opposite reaction torque. And you all know why if you think about a helicopter. When you have a helicopter, you increase the speed of the blades, and if you don't have that tail fan spinning at the right rate, then the body of the helicopter rotates the opposite direction to the blades, because whatever torque the motor is applying to the blades, it must be applying an equal and opposite torque to the body of the helicopter. And so the purpose of the fan on the back of the helicopter is to create another torque which balances that, keeps the blades rotating one way, but stops the body of the helicopter from rotating.